Do you see this? Advanced.
We're told that h of x is equal to 3x. G of t is equal to negative 2t minus 2 minus h of t. F of n is equal to negative 5n squared plus h of n. So we have three function definitions, and two of these function definitions are actually defined in terms of another function, in particular in terms of the function h. And then we're asked to calculate what is h of g of 8. And this can be very daunting, but we just have to remember that all a function is something that takes an input and gives you an output for it. And this is another way, this somewhat convoluted looking statement is another way of saying, look, we're going to take the number 8, and we are going to input it into the function g. We are going to input.
Why do you stop? What's happening?
We're told that we are going to input that into the function h, and what we will have will be h of what we inputted, h of g of 8. So let's just do it one step at a time. Let's figure out what g of 8 is. So g of 8, and I'm going to color code it so we can keep track of things. G of 8 is equal to, well, g of t, we have our definition here. So our input now, instead of 8 is going to be our t. So our input is 8. So every place where we see a t in this function definition, we replace it with an 8. So it's going to be negative 2 times 8, negative 2 times 8, minus 2, minus, and this might be a little daunting, but let's just replace this t with an 8 and then see if we can make sense of it. H minus, let me do it in the right color, minus 2, minus h of,
Wait. H of t. Again, we're going here. Which is h
of 8. Notice, to evaluate g of 8, all we did is everywhere we saw a t, we replaced it with the input 8. Now let's see if we can calculate this. This is going to be equal to negative 2 times 8 is negative 16, minus 2 is negative 18. I'll do that same. So this is going to be equals negative 18 minus, what is h of 8 going to be equal to? So let's do that over here. So h of 8, this thing, h of 8. Now we go to the definition of h. Don't worry about later we're going to input all this business into h again. Just let's worry about it one step at a time. We need to calculate h of 8. So h of 8 is just going to be, well, every time we see an x, we replace it with an 8. It's going to be 3 times 8, which is equal to 24. So this value right over here is 24. We are subtracting it. So we have minus 24, negative 18,
okay.
minus 24 is what? That's negative 42. So this, all of this business
Right there, yeah.
is going to be equal to, did I do that right? Yeah, negative 42. So we figured out what g of 8 is. It is negative 42. So this right over here is negative 42. And now we can input negative 42 into h. So h of, let me do it right over here, h of negative 42, remember, negative 42 is the same thing as g of 8. So this is h of g of 8 is the same thing as h of negative 42. This is going to be equal to, same color, this is going to be equal to 3 times negative 42. 3 times negative 42, which is equal to, this is negative 126. Negative 126, and we are done. So it seemed convoluted at first, but if you just keep track of what's our input, what's our output, and just really just evaluate the functions, it should hopefully be reasonably straightforward. Carter has noticed a few quantitative relationships related to the success of his football team and has modeled them with the following functions. All right, this is interesting. So he has this function, which he denotes with capital N. It's the winning and the input of it is the winning percentage W, and the output is the average number of fans per game. So he's making some type of model that says, look, the number of fans per game are going to be in some way dependent on what your winning percentage is. And I'm assuming his model, the higher the winning percentage, the more fans are going to show up at a game. Now this is W. The input is the average daily practice time, X, and the output is the winning percentage. All right, that makes sense. Probably, once again, probably some type of a positive effect of practicing more is going to create a higher winning percentage. And this other function, number of rainy days are, and then average practice time. Yep, well, the more rainy days you have, well, that's going to lower your average practice time. So I definitely see how practice time P would be a function of number of rainy days. The expression N of W of X represents which of the following? Well, before we even look at the choices, let's think of what's happening. This is another way of denoting, we're going to take X right over here, and we are going to input it into W, and we're going to get out W of X, and then we're going to input that into the function N, and we are going to get out N of W of X. So what does the function W do? What does the function W do right over here? Well, that's winning percentage as a function of practice time. So you input practice time, and it gives you, somehow predicts a winning percentage. Winning percentage. And then you take that winning percentage and you input it into function N. Function N is going to output the number of fans per game based on winning percentage. So this is number of fans. So when you take the composite function, you're actually creating a function that starts with practice time as the input and shows the number of fans that are going to be dependent on your practice time. So this is interesting. So we should look for a choice that says, how does the number of fans that show up at a game, how is that dependent on practice time? X. All right. The team's winning percentage is a function of the average daily practice time. Now that would be just W of X. If they said just W of X, that would be winning percentage as a function of average daily practice time. So I can cross that one out. The average number of fans per game. This is interesting because that's what the final output is going to be in terms of the average number of fans per game. That is the output of the function N right over here. The average number of fans per game as a function of the number of rainy days in a season. Nope, we're not doing that. We're doing it as a function of practice time. You could construct that. In fact, if you wanted to do this, that would be N as a function of W as a function of P of R. So that would have been this choice, where you input the number of rainy days. From that, you're able to figure out practice time. And then you input practice time to figure out win percentage. And then you input win percentage to figure out the number of fans in the crowd. But that's not what we're doing here. We're just starting with daily practice time and getting to fans per game. So let me rule this one out. And if you found this one what I just did a little bit confusing, I encourage you to try to set up a diagram like I just did in the beginning of saying, oh, well,
Yeah.
look, we could start with R to use that as an input to get average daily practice time.
That's easy.
We're told that Phlox is a skydiver on the planet Lernon. The function A of W is equal to 0.2 times W squared, gives the area A in square meters under Phlox's parachute when it has a width of W meters. That makes sense. The function V of A is equal to the square root of 980 over A, gives Phlox's maximum speed in meters per second when she skydives with an area of A square meters under her parachute. All right? Write an expression to model Phlox's terminal velocity when her parachute is W meters wide. And then they want us to evaluate the terminal velocity when her parachute is 14 meters wide. Well, let's just focus on the first part first. Pause the video and see if you can have a go at that. All right, now let's just think about what they're asking us. They want us to model terminal velocity when her parachute is W meters wide. So really, what they want us to do is come up with a terminal velocity, let's call that V, that is a function of W, that is a function of the width of her parachute. Well, we have a function here that gives terminal velocity as a function of the area of her parachute. But lucky for us, we have another function that gives us area as a function of width. And so we could say this is going to be the same thing as V of this function right over here. I'll do it in another color. A of W. And so that is going...
W meter wide. velocity.
To be equal to, keep the colors consistent. Well, everywhere where I see an a in this expression, I would replace it with a of w, which is 0.2 w squared. So it's going to be equal to the square root of 980 over, instead of a, I am going to write, so instead of this, I am going to write 0.2 w squared, because that is a as a function of w. 0.2 w squared. So this right over here, this is an expression that models Phlox's terminal velocity v as a function of the width of her parachute. So that's what we have right over there. And then the next part, they say, what is Phlox's terminal velocity when her parachute is 14 meters wide? Well, then we just have to say, okay, w is 14. Let's just evaluate this expression. So we'll get, we're told that Jalen modeled the following relationships about their bus ride. So there's three functions here. We have their inputs and we have their outputs. So function p, the input is the time the bus arrives, given as lowercase b, and the output is the probability that Jalen gets to work on time. So p of b, all right. Function n, the input is the time the bus arrives, given as k, and the output is the number of people at the bus stop when the bus arrives. So it's the number of people at the bus stop as a function of the time the bus arrives. And then T, centimeters of precipitation, the input is centimeters of precipitation per hour, x. And this gives us the time the bus arrives as a function of that precipitation. Interesting. Now they ask us which of the following composed functions makes sense in this context, and we have to pick two.
Two answers, huh? Yeah. So PTX PTX and NTX كلها both تنفع.
So pause this video and see if you can have a go at it before we work through it together.
Yep,
All right, let's look at this of x, t power. T of x is the time the bus arrives. Function of the time the bus, a function of taking k, which is function put here, and input it into it does not. So so t already know this function and takes function of stuff. So this makes sense. So I like to validate that. So P of v. So this.
Let's do the exercises quick. Bjorn is a very prolific, able to write thousands of pages per day. His assistant modeled a few function relationships below. type AX. I, IPX. The depth D of the submarine in feet below sea level after T minutes have elapsed is given by the function dt equal 20 plus 16t. In a way, the pressure, the function, the elapsed time in minutes, bounds, edge, submarine at depth, minutes, elapsed. Okay, this will come here in this x and this x, so this will be so it's gonna be No. No, no, wait. Yeah, let's give 7. I'd go with this as the closest. Okay. So P-I-C-R. P-I. Well, okay. This must go here. So B-I. No B-I. Okay. And then we get number of cartridge, number of, so ISR, no ISR, in a way. No S, no S, IPX, no. Why are you telling me to choose 2 answers? SPX, number of cartridge, number of pages. SPX, no, because this, okay, this will give number of pages, okay, inside it. So this, and this needs number of cartridges. So it's not gonna be SPX, IPX, okay, PX gives number of pages, IPX, I, because this is getting pages and this is number of pages, so IPX, and this PIX, PIK, okay, K, gonna give number of cartridges, PIK, give number of cartridges, not gonna go here, no way, no way, PI, no way, this, what do we got, SPX, PX gives the number of pages, nope, and SIK, IK is gonna give number of ink, and this is needs number of other plays on football team relationships. NWX. Achieve the following NWX. So the function get WX getting me winning percentage. Winning percentage gives me average number of fans per games. So okay, this is enough for today.